Hello everyone, my name is Sam van Damme. I'm a PhD researcher at Ghent University and IMEC. And in this presentation, I will show you the content of our paper, Effects of Haptic Feedback on User Perception and Performance in Interactive Projected Augmented Reality. Interactive extended reality, as you all know, is gaining more and more attention in both industry and academia, especially for entertainment, such as gaming purposes, but also for other applications, such as augmented reality rehabilitation exercises, immersive virtual reality training, for example, for first responders, and also OmniTouch, which is a technology that enables to actually turn about every surface in a touchscreen a user can interact with. Now, in the most recent years, these kind of experiences have been enhanced with haptic feedback, both in terms of vibrotactile and force feedback. Now, despite this evolution, the influence of this haptic feedback on end user perception and experience is still rarely explored, which is the motivation of this paper. If we have such an interactive extended reality system, be it augmented or virtual reality, there is of course a certain perception of the end user, as well as a certain performance in case the user is performing a certain task, for example, for virtual reality. Now, when streaming this over the network with some network distortions in place, such as latency, this of course affects this perception and performance. Now, the question we are asking ourselves is if we add a haptic feedback system to this multimedia system, how would this influence or change this perception or performance? More in particular, we asked ourselves three research questions. First of all, does haptic feedback have the possibility to reduce the duration of completing such a task? Does haptic feedback reduce the number of errors made while completing this task? And third, how does haptic feedback influence or in the best case improve user experience? Now, how did we do this? We created the following setup in which we attached a projector to the ceiling to project virtual objects to a given surface, such as a table. And by means of finger tracking, the user is able to interact with these virtual objects to perform certain tasks, where the finger tracking is provided by means of the Intel RealSense depth camera, which is attached close to the projector. In addition, we also included the Noitum Hi-Fi virtual reality gloves into the system to give the user vibrational feedback while performing the tasks. And we also implemented the possibility to artificially induce a certain latency between the finger tracking and the visual representation of the virtual objects on the surface. Now, to evaluate this, we also created three different user tasks. First of all, there is Simon Says, the well-known game in which the user gets a certain target color, which is orange in the example here. And then the user simply has to press the according color out of the three options on the bottom as fast and accurate as possible. A second game is a trace a line game. Here the user has to push the start button in the lower left corner, and then with his or her index finger follow the given line as fast as possible to the endpoint in the upper right corner without deviating more than a prior determined threshold of the line, which we fixed at 10 pixels for this work. Now the third game is the obstacle course game. Here the user has to guide a given circle through a maze to the drop zone in the upper right corner, which he or she can do by pinching the circle to deform it and to drag it in any given direction. Of course, the user should try to do this without touching the walls of the labyrinth. Furthermore, we also included some haptic and visual feedback into the system. In terms of haptics, we provided the user with a low frequent and low intense vibration scheme of 200 milliseconds, followed by a 2-second pause whenever the user is performing the right expected actions. From the moment the user is making a mistake or performing an error, this changes to a 500 milliseconds vibration followed by a 1-second pause. In terms of visual feedback, we always make sure that respective elements, such as the buttons in Simon Says, the line or the circle are colored green whenever the user is performing the right action, and that is colored red whenever an error is made. To evaluate this, we collected 23 participants, which we divided in 2 groups. One control group consisting of 11 subjects, which performed the task by means of visual feedback and finger tracking only, without the haptic feedback of the gloves. And then a second test group of 12 subjects, which was also given access to the Noitum High 5 virtual reality gloves and of course their feedback. 6 of these subjects identified as female, the other 17 as male, and their ages are between 19 and 44 with an average of 26.3. The actual test procedure consisted of 2 phases. First of all, every subject gets a training phase in which he or she can play every game once without any latency between the actions of the user and the visual feedback on the surface. And then in the second phase, the main phase, every user plays each game 4 times in addition, in which the latency differs between 0 seconds and 2 seconds, in which we make sure that every combination of game and latency is visited once by each subject and in random order. In terms of evaluation, we provided both subjective and objective evaluations. In subjective manners, we provided a pre-session questionnaire in which we polled about age, gender, and handedness. Also Ishihara tests to test for color blindness, which is of course relevant in the context of the visual feedback, and also towards prior experience with projected augmented reality, haptics, and subjective evaluations. In addition, we also polled about technical proficiency, which users self-assessed. Then after each task, we asked the user to grade the perceived latency on a 1 to 5 scale. And after the whole experiment, users were asked to assess the influence of haptics on the reduction of errors and duration, and also on intuitivity, where of course for the control group, it's about an expected influence, and for the haptic group, which indeed used the gloves, it's about the actual perceived influence. In terms of objective evaluations, we monitored the duration, so the time needed to complete each task, as well as the number of errors being made. Which brings me to the results. First of all, in terms of subjective perception, there are 2 things that I would like to point out. First of all, in terms of perceived difficulty, it's clear that for both groups, there's a significant difference between the obstacle course game, which is perceived as much more difficult than the other 2 games, which is of course interesting to interpret further results in terms of difficult versus easy games. Second, also interesting to see is that for the easy games, the perception of the haptic group is that it has a high influence on reducing the errors in the games, while the expectations of group A in this regard are much lower. Towards duration and intuitivity, we haven't seen any significant differences between both groups. In terms of latency perception, it's interesting to see that for the Simon Says game and the obstacle course game, we don't see any significant differences between both groups, while for the Trace the Line game, the haptic group, so group B, is consistently and significantly perceiving the latency in the system higher than group A, which is of course something intuitive, as this synchronization between haptics and visuals emphasizes any latency in the system. But it's of course interesting to see that this doesn't hold for the other 2 games. In either way, it's important that the inclusion of haptics can increase the attention to any latency in the system and thus influence the user experience. Then in terms of objective evaluations, for the two easy games, let's say, so Simon Says and Trace the Line, we haven't noticed any significant differences between both groups. While for the obstacle course game, we do see a significant improvement in terms of errors and duration when including the haptic feedback into the system, which is especially emphasized for higher amounts of latency, thus the 1 and the 2 second values. Now, this is an interesting observation because if we look back at the subjective perception, the two easy games were actually perceived to benefit more from the haptic feedback than the obstacle course game, while the objective values show it the other way around. In addition, in terms of duration, the haptic group didn't show any difference in perception towards duration reduction, while from the objective values, it's clear that the obstacle course benefits much more from the haptic feedback than the other two games. Which brings me to the conclusions of this work. So first of all, we have seen that haptic feedback reduces the execution time and the number of errors on tasks perceived as more difficult, so in this case, the obstacle course game, and that this effect is enhanced with increased latency, but not reflected in the subjective beliefs. Second, we also noticed that latency is consistently perceived higher in the haptic group for particular tasks, in this case, the Trace the Line game, which of course can increase awareness to reduce network performance and thus influence the end user experience. Towards future work, you would like to conduct a larger study with more test subjects and a higher variety of tasks to see whether this finding still holds. And we're also thinking about including psychological signals for further perception analysis. Which brings me to the end of this presentation. I thank you very much for your attention. And of course, if you have any further questions, please don't hesitate to contact me via the email address shown on the screen. Thank you very much.